Alright, we're going to continue working through the worksheet on balancing forces and actually getting some numbers. You'll notice that again the same process that we used before is going to be the same process that we follow now. We draw a force diagram, we decide if it's in equilibrium or not, we write out equations, and then we put the numbers in. Okay? Remember that the equations are being built from our force diagram. That's why we have to do the force diagram first. The equations don't just come out of nowhere or out of a memorized set of equations. Okay, so let's go ahead and look at this. A student is pressing a book between his hands, holding it vertical in the air. Now this says see Mr. Bywater, but you can't really see me right now, so let me just draw a picture. Okay, there's one hand, okay, pushing on the book. Okay, there you go. There's your book. And here is the other hand pushing on the other side. How's that? There you go. Two hands pushing on the book from either side. Alright, just like that. They're pushing horizontally. Okay? And so the question then is, let's draw a force diagram. Okay? Please pause the video and try it on your own. Alright, welcome back. Here we go. Let's see if we can draw a force diagram. Here is my book. Okay, so this is going to be my left hand, and this is going to be my right hand. I'm obviously doing this with respect to I'm looking at those being my hands. If you hold your hands up in front of you and hold the book, you'll see the same thing. Your right hand is on the right, your left hand is on the left. Woohoo, big surprise, right? Okay, so here's your book. We obviously non-contact forces first, so gravity is pulling down. Again, that's the only non-contact force that we have. The only other ones that we've talked about are electricity and magnetism, and obviously the book is not magnetic or full of negative charge, and so basically you don't have to worry about either of those. Now let's look at contact forces. First, tension. Is there any ropes or cables? No. Second, friction. Okay, well let's consider that. If there was no friction, what would happen to the book? Well, the correct answer is it would slide down out of my hands because there would be no friction between my hands and the book, and so it would just slide down, regardless of how hard I push on it and how hard I try to hold it. Okay, it would just slide out. Now, if it would slide down, that means that friction has to be pushing up on it so that it doesn't do that to balance the forces. Now we actually have two sets of friction, right? I've got friction with my left hand and I've got friction with my right hand. So I'm going to draw both of those in. So force of friction left and force of friction right. Okay, so I've got those forces. They're a little bit shorter than the force of gravity. They should be about half. Okay, now I've done friction, I've done tension. The only one I've got left is normal forces. Is anything touching my book? Well, yes, my left hand is and my right hand is. Well, right hand is pushing in which direction? It's pushing perpendicular. Even if I was pushing up at an angle, right, we're not considering the angle because normal forces are always perpendicular to the surface. So it would always be perpendicular to my hand. So here we go. This is the force of my right hand. Okay, my right hand is pushing towards the left, right? Here would be the force of my left hand. My left hand is pushing to the right. Okay, so there's all the forces. There's nothing else touching the book, so there can't be any other contact forces, normal forces. So we're done with our force diagram. Okay, I invite you now to answer question B. Are the horizontal forces in equilibrium, and how do you know? Please pause the video. Alright, welcome back. Let's look at the horizontal forces. I've got the force of the right hand, the force of the left hand. Are they in equilibrium? Well, equilibrium, again, means that the velocity is constant. Is my book speeding up or slowing down or changing direction horizontally? And the answer is no. It's at rest and it's staying at rest. Therefore, the horizontal forces are in equilibrium because the book is staying at rest. Staying at rest. Obviously, I can't spell staying. Okay, let me try that again. Stay. I did it again. Staying. Alright, there we go. Now, let's look at C. Are the vertical forces in equilibrium? Please try to answer that by yourself. Pause the video. Alright, so hopefully you got that again, yes, the vertical forces are in equilibrium because again, the book is, I got it that time, staying at rest. Okay, you could also say that the forces are balanced, right? You know the forces are balanced because it's not accelerating vertically, right? Okay, let's go on to question D. Write an equation using only symbols for the horizontal forces acting on the object. Again, please include appropriate positives and negatives, and secondly, any trig if necessary. Please pause the video. Alright, here we go again. Horizontal forces. Sum of the horizontal forces. There's only two of them, right? The force of your left hand, which is pushing in the positive direction, and the force of your right hand, which is pushing to the left, so we're going to call that negative, and so that should equal 0. Okay, there you go. Alright, now remember that those are both normal forces, right? Those are normal, everyday, ordinary forces, so that's the normal force of my left hand and the normal force of my right hand. That's going to be important when we come to E and F. Okay, now let's go on to E. Write an equation using only symbols for the vertical forces acting on the object. Okay, please pause the video and write your equation. Alright, so here we go. Sum of the forces in the y direction is equal to the force of friction on the left hand. Oops, that shouldn't be a big L. Okay, sum of the forces on the left hand, which is going up, so that's positive. We've got plus the force of friction of the right hand, also going up, positive. And then we've got the force of gravity, which is going down, so minus the force of gravity. And that's it. There's no angles, so I don't need any trig. There you go. Okay, please try letter F, pause it, and then we'll do it. I'll walk you through it. Okay, so now let's put our numbers together, right? The book weighs 31 newtons, and the coefficient of static friction between the hand and the book is 40.40. Insert numbers and solve for the force that each hand must exert on the book. Okay, so I'm looking at these right here, letter D, right? The force of the left hand and the force of the right hand. Right now, all I know is that if I subtract them, they equal 0, right? Which means essentially they're equal to each other, right? So I could do that. I could add the force of the right hand to the other side, and that would just give me that force of left equals force of right, right? If I add that to both sides. Now, if I look at my equation for the vertical forces, which since it's in equilibrium is equal to 0, then let's now look at these and see if we can get something helpful out of that, right? Because this, we don't have any numbers, so that's no good. So let's see if we can now put that in to this equation. Alright, so let's take the force of friction of the left hand. Now it doesn't tell me what the force of friction is, but it does give me the static friction coefficient. Okay, so the friction coefficient, if you'll remember we said in class, the force of friction is equal to the coefficient times the normal force, right? Okay, so let's put that in. So the frictional force of my left hand is going to be equal to the coefficient of friction times the normal force of my left hand. Okay, now the normal force of my left hand, that's this right here, right? That's how hard my left hand and the book are pushing against each other. So I'm going to rewrite that as mu times the normal force of the left hand, which is FL, which was referred to here in part D. Alright, then I've got the frictional force of my right hand. Okay, again, that's going to be the coefficient of friction times the normal force of the right hand, which is this one right here, FR. Okay, minus the force of gravity. Now it tells us that the weight is 31 newtons, so it's going to be minus 31 equals 0. Now I can go ahead and put in numbers for this. So it'll be 0.4 force of the left hand plus 0.4 force of the right hand minus 31 equals 0. Okay, I'm almost ready, except I note that I still have two variables. Okay, but you'll remember that down here we said that both of those normal forces were the same. They had to be to balance the horizontal forces. And so now we can replace one with the other. It doesn't really matter. I'm right-handed, so let's replace left with right-handed. You can do the other if you want, but I'm going to rewrite this. Since the left-hand normal force is equal to the right-hand normal force, I'm just going to write that as force of the right hand. And write everything else exactly the same. Yep. So there we go. Now we can solve the problem. We'll add together like terms. So that's 0.8 times the force of the right hand minus 31. Let's go ahead and add the 31 to both sides. So that will equal 31. Divide both sides by 0.8. And we get 31 divided by 0.8, which is 38.75. So that is the force exerted by the right hand. The force exerted by the left hand is the same thing, 38.75 newtons. Hopefully that kind of makes sense. You can kind of start to see now how we're going to be relating the horizontal and vertical forces, right? Remember with kinematics we were able to relate them through the time. Remember how the time always put those two things together? Again, there's going to be certain things that relate the horizontal and vertical forces, and this is one of them. Friction is that key that relates perpendicular forces in some cases. So there you go. There's the answer. Let's go on to question number 3.